Okay, students, welcome into our very last lecture, if you will. I kind of jumped the gun. I have the whole presentation ready to go here, but let me just hop back and sort of show you what we got going on for this module. It's the usual things. So let's look at the discussion board real quick. You can see I haven't even made this public yet. I'm recording this on Sunday afternoon here. So just two questions for our discussion board. We're back to a little video in question, but you'll also want to keep in mind some of the stuff we talked about last week with winds and the Coriolis effect and whatnot. Especially for question two will have to deal with the Coriolis effect. You'll have to kind of incorporate that into it. And then number one, why don't hurricanes ever form in the polar latitudes? We will cover that in the lecture, but it also gets covered in the discussion board video there. So just be aware that that's available to you. Okay, so let me hide this little thing at the bottom here, and I'm going to keep going. So let me hop on back. All our familiar stuff here. Discussion board, you can hop to it. Link to CK12, let's just look at that real quick. I think you'll be pleasantly surprised. It should be live, but let's check it out. Let's see if it's all ready to go. So this being our last section here. Holy moly, man! It all happened so fast, didn't it? I hope you cannot hear, but they just started right outside my apartment to do some maintenance work, and so there's a leaf blower and whatnot. We'll see if it interrupts this lecture here. So I'm going to make our last unit live. I'm assigning this. It will be absolutely 100% due on May 6th, no later than that, because that's when I got to get the grades in. So let's look at this last one. So for May 2021, you have made it all the way through, and to reward you for all your hard work, look at this. Boom, 2 sections. That's it. Just hurricanes and then the quiz. So you're going to be able to get this done like that. Remember, if you finish this during the week and you don't want to attend the Zoom, that's totally fine. Send me a message, let me know, and your semester is done. Just a little section on hurricanes, a hurricane quiz. Make sure for that quiz you're going to be using not only the CK12 stuff, but also the stuff you'll learn in the lecture today. I haven't looked at this lecture in a long time, in about a year, figuratively. I did a couple updates to it, but I didn't really have time to practice it. If you could believe it, I actually do kind of practice some of the lectures before I go into them. But this one, we're just winging it. We're going for it. It's the last class of the semester, and we're just gonna ride the pressure belts, ride the jet stream here, and get hurricanes done and over with. So I have it on here. The title of this lecture is just "Behold the Hurricane." I think they are incredible because they're so incredibly powerful. But also, the little title from this comes from one of my favorite songs, one of my favorite artists. One of my favorite artists is Brian Fallon. Not that you need to know this part, but he plays not only in the Gaslight Anthem, he's a solo artist, but he also put out an album with a band called the Horrible Crows. And on there was a song called "Behold the Hurricane." And I thought it was a great song. I was like, oh, well, what an appropriate title for this here. So let's do a couple things. Let's turn on that awesome laser pointer feature. Let's make this full screen, and let's behold the hurricane, because it is an amazing, amazing force. So once upon a time in the tropics, that's where we're starting here. So our story begins in the swath of the earth that resides between the latitudes of 23.5 degrees north and 23.5 degrees south. So let's look at this in here. So this is that area in there. We're looking at this, Tropic of Cancer, Tropic of Capricorn area, everything in between, and in these, equatorial areas where we have really high temperatures. It gets really hot. You have usually these areas of low pressure where air is just rising up because of the, direct sunlight that is, making those molecules speed up faster. They spread out, they become less dense, and they rise up. Those convection cycles we have been hammering this entire semester. So tropical weather, we need to understand it a little bit. So in the tropic regions, the weather is much different than at the mid-latitudes, like what we experience. So seasonal and diurnal changes, which means during the day, are minimal. So here, especially, it's say if you live up in Apple Valley, or I shouldn't say specifically Apple Valley, but if you live in the high desert, or even if you live more inland from the beach, we experience pretty heavy diurnal changes, meaning that, like, especially if you're in the desert, it could be like 110 degrees during the day, and at night it can dip below freezing. That's a huge temperature swing. Now, down at the beach, it's not so dramatic. If you look down, like, Huntington Beach or Newport Beach, like their weather forecast, you'll see a lot of 70s, 80s, 70s, 80s, maybe in the 60s. But those changes aren't very dramatic. And same with the tropical regions. So we have down there, we have high temperatures because we have the direct sunlight, and we have high humidity, which means, very moist air. Because if we look back, we can see, holy moly, there's a lot of ocean in this area. There's the dog once again, right on cue. Has to steal my thunder. Has to go sashay off and just leave me here. Whatever. But anyway, so the high temperatures and the high humidity leads to cloud formation, because this warm, moist air will rise up, and it kind of, once it reaches the higher points of the atmosphere, it will condense back into water droplets and create clouds. And so it leads to what are called cumulus clouds and a lot of afternoon thunderstorms. If you've ever spent time down in any of these areas, like especially like Central America-ish, or if you've ever been like to Indonesia, these areas in here. I have a buddy who does like a lot of work in some of these African countries like Kenya and Ghana and whatnot. And so these areas in here, they will experience like these really intense afternoon thunderstorms. The closest thing we can kind of compare it to is, like during like the summer months, if you look like either over the San Gabriel Mountains, which are up here, I'm pointing back this way, because that's the general direction they are, or over near like Riverside, you'll see these huge clouds, just like this one, like start to form. It's kind of like that. You have this air that's heating up, rising up, and then condensing in the clouds in the afternoon. So with our tropical weather, occasionally these thunderstorms can become so loosely organized. I shouldn't say so loosely organized, but they will be loosely organized into what's called a squall cluster or a squall line. So essentially, it's just like a line of these thunderstorms, almost like a wall or a front moving this a certain way. And so in the tropics, the hotter, more humid months, which is like summer and early fall, and like little hint, that's what we usually call hurricane season. Teaser there, right? Teaser there. They're usually marked by increased cloudiness and precipitation. So these are the hotter, more humid months. So we see a lot more of the low pressure systems forming and creating these clouds and thunderstorms and precipitation. So the winds in this area, and it's important, we talked about them last week, they generally sort of blow from the east, so from the northeast or the southeast. So they're coming from that general direction. And so we can kind of see here what this kind of squall line would look like. And so you have this sort of like cold pool of water that's, the more dense air, so it's going to be down below. And then we have the hotter air rising up above. And as we have these sort of pressure systems move, we get these, big dramatic cumulus clouds with almost like these trailers here. But anyway, when it forms like in this big line like this, we call it a squall line. So with that, this is a really cool map. This is like a current map, an ocean currents map. And it sort of shows us like how these currents in the ocean flow typically. And so global wind patterns, which we talked about last week, the ones that are on like the bigger scales between like certain latitudes. And if we look here, we can see those sort of broken up between 0 and 30 degrees here. If you look, there's essentially, certain currents that sort of exist in this area. Between 30 and 60, we're looking at some of the ones up in here and down in here. And then at the poles, well, it gets a little more complicated because of a smaller area to move around. There's also land masses. But anyway, so these are the ocean currents that we're sort of looking at. And so the global wind patterns that are a result of the differential heating of the planet, which we talked about, are also factored in with the Coriolis effect, which we looked at last week, where since certain parts of the planet are spinning at different speeds, it sort of creates this drag or this perceived motion and this sort of spinning effect on fluids, whether it be water or whether it be like the air. And so meteorologists use what are called streamlines to show where surface air converges and diverges. And then sometimes these streamlines are disturbed by what's called a tropical wave. And so this tropical wave is a weak trough of low pressure. So this is a wave not in the ocean, but in the atmosphere. But it acts in sort of the same way. But one of the keys there, we want to make sure we know that it's low pressure. And so this was a little picture I snapped from a textbook of mine. But these tropical waves, they are so remember, we want to think of air as like a fluid that flows from high pressure to low pressure. Anytime there's like that pressure difference, there's going to be this gradient going from high to low. And so the thing about these waves is that they have a wavelength of up to 1,500 miles, meaning that in order to go from like a peak to peak or trough to trough, it would take about 1,500 miles. So they're very, very long or very, very high wavelength waves. And they travel from the east to the west. So they're starting sort of on this western coast of Africa here, and they're moving from the east to the west. And you can kind of see these flow lines here that kind of show us the direction of movement. And so the western side generally has fair weather, while the eastern side has the thunderstorms and showers. And this is due to the divergence and the convergence of air as it interacts with the trough. Now, we've talked about those terms when we're talking about plate tectonics, diverging meaning like going away, converging meaning coming together. And so this can sort of start to be the baby steps or the seedlings of a hurricane. And so as, the air flows this way, all this, this low pressure trough here. So you have to think about the air is kind of going this way, then there's this low pressure trough, and then it's sort of going back around. So in this area right here, these, which one I call it? I'll just say winds, these, this wind that's blowing this way is kind of converging in this area, coming together. And then once it passes through that trough, it begins to diverge on the other side, which we can kind of see. And when it diverges like that, you're really going to get the fair, beautiful conditions. And where it's coming together like this, so you have this low pressure trough bringing air up. You would get the thunderstorms and the showers like we were talking about before. And so now let's just begin to talk about the anatomy of a hurricane, because a hurricane is very robust. It's a huge system, and then there's different parts we want to talk about. So as always, we want to define a hurricane. And you can see some of these symbols over here. So if you ever see these on like a weather map, when you're just hanging out on a Friday night studying your weather maps, if you see one of these symbols, this is a hurricane. And then we also have this number here to denote the category, which we'll get into. And then on the right here, this is the logo for the National Hockey League team, the Carolina Hurricanes. And you can kind of see why they chose that logo. Very clever of them. But anyway, so a hurricane is an intense storm of tropical origin. So that's an important part. We know it starts in the tropics. And it has to have sustained winds of at least 64 knots. Or if you're not a sailor, like I am not, that's a funny little joke. I am not a sailor. 64 knots, not a sailor. That's about 74 miles an hour. But the thing there is that it has to be sustained winds. With the Santa Ana winds, we often get a gust that are 80 miles an hour plus, but we don't consider those a hurricane because it's just a burst. It doesn't stay going 80 miles an hour for a prolonged period of time. Now, you can have much higher gusts, but these typically form, I shouldn't say typically, they form over the warm North Atlantic and the eastern North Pacific Oceans. The whole idea is we're going to have ingredients for a hurricane here, and one of the most important ones is this warm water. So this is a little plane. This is a little picture from a plane. I didn't take it. I would never fly that close to a hurricane. Those people are absolutely insane. But you can kind of see a little bit of like the pattern of direction of flow. You can kind of at least get appreciation for the magnitude and the size of these things. But so hurricanes are made up of what are called intense convective clouds. So we'll talk about that in just a second. And they can grow to be over 50,000 feet into the air. That's huge. It's monstrous. When I say behold the hurricane, behold it. It is powerful. It is insane. But anyway, so if you're so we have this term hurricane. You've also might have heard like a typhoon or a tropical cyclone or a cyclone. And that's just the difference of almost like the area of where it's being formed. Kind of like, so I have a lot of family back in like Michigan, Wisconsin, and Minnesota area. And if I go out there, like normally if I was going to get like some pizza or something, I'm going to get some pizza and a soda. And they're with them soda. What is that? They call it pop. And so it's the same thing. You just call it something different based on the area that you're in. And so these hurricanes we're going to see are pretty much the ones that form in the Atlantic. The western North Pacific storms that are exactly the same, form the same way. They're just called typhoons. And in India, they call them cyclones. And in Australia, they call them tropical cyclones. Everybody has to be different and have their own way. But anyway, the international consensus is to call these a tropical cyclone. That's like if you go to the National Oceanic and Atmospheric Administration website, they're going to say the international consensus, and they're right, is a tropical cyclone. But we're going to use the term hurricane because that's what they are. So anyway, so this is Igor. This is Hurricane Igor. This was an actual hurricane that existed, and we can get to see some of the parts of it. But we want to talk about the anatomy once again. So this was a very average hurricane. So this isn't one of those, Katrina-sized ones or like Hurricane Andrew-sized ones. This is just a very mediocre, very average hurricane. And what we do when we sort of break these down into their anatomy is we look at like the different sections of the hurricane and how their characteristics are different. So the thickest cloud cover has a diameter of about 310 miles. So if you're looking at going from like this thickest cloud cover areas in here, you're looking like 310 miles. That's like having there farther than the drive to Vegas. That's a pretty wide diameter of this hurricane. And like I said, that's about average. So that's not even our biggest ones. And then the eye is the area of relatively clear skies where you have the low pressure center, which is rising up, which is why like the eye is like perfectly calm and like beautiful and clear because you have the pressure rising up, which means you usually have like fair skies and whatnot. But it is relatively clear skies. It's about 25 miles in diameter, which is very, very average. So like the eye, which is right in here where the red dot is at the moment, and then around it is what's called the eye wall, because in the eye it'll be clear and calm. And then the wall surrounding that, where the rain bands start, the thickest cloud cover, is called the eye wall. And so the surface pressure within the eye is very, very low. Hardly any surface pressure because that's where the low pressure trough is sort of formed around, and that air is rising up, creating sort of clear conditions. Now, we have these spiral rain bands, and you can sort of see the annotation right there, but they are just sort of spinning around the eye. and depending on where it is, the direction that it spins, this is where the Coriolis effect comes in. And so you have these spiral rain bands that are just going around the eye, circling around. They're very thick clouds laden with moisture, creating a lot of rain, a lot of wind. And so these are areas of high precipitation, which is rain, which swirl about the eye of the hurricane. And so the surface winds increase greatly as they blow counterclockwise and wrap themselves around the eye. So as they're sort of spinning around here, they're just whipping these super intense winds around. And surrounding the eye is the eye wall, which we just briefly talked about, but it's just a ring of really intense thunderstorms. This is where, the very beginning of the destructive parts of the hurricane. But that eye wall is just super heavy precipitation, so a ton of rain, and the winds are very, very intense. And this whole area, this eye wall area, can go up to 59,000 feet above sea level. That's, you're talking well above where airplanes fly. So it is an intense elevation that they can reach. And so here's like a nice little cross section of a hurricane there. So if we approached this cross sectional view from the left going to the right, so the sky say if we're like sailors over here, we're sailors on a boat and we're going this way, and first the sky is going to become overcast. It's going to be like that sort of like thin cloud cover, and you would notice if you had a barometer that the pressure would start to drop as we're starting to move this way, and the winds blow from the north and the northwest. They get faster and faster, so they're coming in this way as they're sort of coming around, and then as we approach the center, these winds can create waves that are 33 feet high. So if we were coming in this way, these swirling bands around here are creating huge, huge waves as the hurricane is gaining steam, if you will. And you also have the increased rainfall. And then as you reach the eye, the winds will die out, the skies will become clear, and then you got to go through the other side of the hurricane. So just when you think you're done, you're not. There's still more coming around. All right. And so we say the hurricane heat machine, because this is the fuel. This is what hurricanes need in order to survive. They need heat and water. Pretty much the basic ingredients. So near the surface, this moist tropical air flows inward. So we have this area of low pressure in here, right? So low pressure in here. And as this air runs out this way and it starts to sink back down, well, it gets, you have this area of high pressure. I'm sorry. Sorry. But you have this area of high pressure that will be pushing down. And as these sort of creating like this low pressure here, and as this, we want to think of these as like convection cycles. As these sort of get pushed down, we have this area of low pressure is going to have the other air sort of like take its spot, flow from high to low. And so if we have the high pressure up here, the low pressure down here, as soon as the pressure gets high, it's going to sort of cycle back in, like those convection cycles that we were looking at. And this sort of graph down below kind of shows us how that looks like graphic-wise. So the air pressure, the surface air pressure, as we approach the eye of the hurricane, it dips. So we have very low pressure at the eye, and then it increases as we go out. Well, because of this, big old trough of low pressure, this high pressure is going to take its spot. So therefore, since it's so low, you're going to have this huge rush of wind. And we can see here the surface wind speed is going to increase. It gets to the eye and it virtually drops off because it's just all low pressure rising up. And it's not until it's created this sort of vacancy here that other air rushes in to take its spot. So close to the eye, the air rises due to the low pressure. And as it makes its way to the cooler parts of the atmosphere, the water vapor condenses into these huge thunderclouds that produce massive amounts of rain. And you can get up to 6 inches in an hour, which is nuts. That's a lot of rain. So at the top, the mostly dry air flows outward and away from the center in what's called an anticyclone. But we won't get too far into that. So the sinking air creates a slightly higher pressure. So as the air starts to sink, it's creating slightly higher pressure at the top of the storm. And it sort of initiates a downward motion of air within the eye. And this descending air warms up via compression, meaning that like as air sort of comes down and sort of gets packed together, it gets like superheated. Like if you ever had like one of those hand bicycle pumps, and then like if you've like pumped it for a while, you feel it start to get like really warm and hot. It's because you're compressing all that air and it heats up. So the descending warm air via compression gives the eye its signature warm air and no convective cloud. That's why it's clear right in the center. And the surface air that is rushing in is heated up. So kind of like our Santa Ana winds, as it rushes in, it heats up from the overlying ocean, which is very hot from being in the tropics, and that the surface air temperature stays very uniform throughout the hurricane. So if you're at the surface, as the hurricane moves across, the temperature is going to stay relatively the same. So the hurricane recipe, notice this guy over here. Believe it or not, I put in that text box. That says delicious. That is that's some high quality graphics I got going there. But anyway, so here's what you need for a hurricane. You need, I'm not going to go with the parts. Yes, I will. You need 1 part tropical waters where the wind is light. So tropical meaning has to be warm waters. The wind has to be little to none. So that way we don't have like air masses sort of running into each other. You have to have 1 part of high humidity, meaning you have to have a lot of moisture, which comes from the sun heating up the ocean, creating moisture to go into the air. I'm sorry, I got a little itch on my nose. And then 1 part of the surface water temperature being 80 degrees Fahrenheit or greater over a vast part of the ocean. And that's pretty intense. 80 degrees, like the waters in the tropics. It's not like it's the waters off of our coastline. The waters off of our coastline are very, very cold, around like 50 to 60 degrees. But these are like 80 degrees, and this was what the hurricane needs to live. And it needs to mix in a large ocean. So you take all these ingredients, and it has to be this large area where they can sort of have time to form, continue to have its fuel of water and heat. And so you mix all those, like I said, preferably in the subtropical North Atlantic or Northeast Pacific in the early summer and fall, that August, September time, which you are not too far away from. So it means we're coming up on hurricane season. So we have these stages in development. So like anything, hurricanes have a birth, a maturation, and a death. And the first stage is just what's called a tropical disturbance. That was that tropical low pressure trough that we saw in the very beginning of the lecture. And it's this mass of thunderstorms, just that line of thunderstorms, that squall line. That's how it usually starts. So you know the song, if you've ever heard the song by the band Toto called Africa, they say like, I bless the rains down in Africa. They're like blessing hurricanes. Those are baby hurricanes and they're blessing them. What are you talking about? Anyway, so the second stage is a tropical depression forms. When they say depression, it's not like it's sad or anything, but it's depression because it's a trough of low pressure. And so as that air is heating up and moving out, that's creating a low pressure system. And after that, winds begin to increase because then we have the air rushing in to replace that low pressure. And we get to around 23 to 39 mile an hour sustained winds, not just burst, but sustained winds. And then the third stage is a tropical storm that develops. If you've ever heard that term, they say like, oh, we got tropical storm so-and-so forming off that may turn into a hurricane. Well, it's just not quite there yet. It hasn't reached those conditions. But the tropical storm develops, and then the winds become between 40 and 74 miles an hour, and now it gets a name. So before, though, they might call it, oh, this is tropical depression, 19-A2. That doesn't sound very fun or exciting. But once it starts to hit that area where it's getting between 40 and 74 miles an hour, now it gets a name. Now it's Tropical Storm, Jason or something like that, or Tropical Storm Cindy or something like that. And we'll get into how they name it in just a little bit. And if the sustained winds reach 74 miles an hour, behold the hurricane. You have a hurricane in its entirety. And so these are ways that we sort of measure these monsters. The category being 1 through 5, kind of showing you the wind speed, going from 74 to 95, and all the way up to 155 miles an hour plus. And that's sustained winds. That's not really survivable if you're standing out in it. You begin to feel like your skin just sort of rattle around. I watched like a little video on it, and it was not the most entertaining video, but it was kind of neat to see the different stages. But one thing we're going to talk about pretty soon here is this storm surge. This does most of the damage during a hurricane is a storm surge, and that's how high like the ocean sort of rise because of the wind pushing the water against the land. And so, just not too long ago, just this past hurricane season, we had a couple of them reach Category 5. That's really intense winds. So it's called the Saffir-Simpson Hurricane Scale. And so you can sort of see here the different categories, 5 being the highest, 1 being the lowest. You can always come back to this if you need to check it out some more. So I say the devil is in the details, and what I mean by that is that most of the damage and loss of life during a hurricane does not come from the winds, typically. Now, the winds will do a ton of property damage, but the highest winds usually occur on the eastern side, the east eye, or eastern side of the eye. And this is due to the convection of the system and the addition of wind speed to the usual winds at that latitude. So we usually have winds at some of these latitudes, but then you add in this low pressure system and the winds become even more intense. And then you get what's called a storm surge. And so as these hurricanes are moving across the Atlantic and coming towards Florida or Puerto Rico or those areas down in there, it starts to push the water up along the coastlines. And so as the water on the eastern side gets pushed along with the storm, it piles up against the coastline and raises the sea level several feet. And so this drop in pressure, also there's since we have this warm air, the drop in pressure allows water to sort of rise up, and because there's not as much pressure pushing down on it. And that's just another factor. So the drop in pressure adds to it, and it can even get worse if it's timed with the high tides. So these sort of all come together in horrible ways, especially if they're all happening at once. And so with Hurricane Katrina in 2005, there was a 28-foot storm surge, which means that the regular sea level, now it was about 28 feet higher, which that's what allowed all that water to come in. Like New Orleans and Louisiana, a lot of it is already below sea level. And so the levees that they had built up could not stand this. You could not have even prepared for a 28-foot storm surge. So here we go. Here's the diagram of that. So as this storm is moving this way and spinning in such a manner, it pushes that water up. And this is the wind-driven surge. And then the pressure-driven surge isn't that much of the total, but it's still significant because this low pressure here allows this water almost like to kind of have like a hill, as opposed to the higher pressures that are sort of pushing this side down. So this is a great visual if you ever want to take some more time on it. And so this is what the storm surge can do. It pushes that water in, and it just devastates areas. It floods it all on out. It messes with like sewer systems. So sometimes you get these backups of sewage, which creates like these just horrid conditions. It's like this toxic soup that's now just sort of flooding everything. And this is a good visual for us in terms of understanding like how much different the temperatures are in different latitudes. So this is a sea surface temperature map, and you can see right in these equatorial latitudes, these tropic latitudes, the ocean is much hotter than it is in other areas. And so this is the fuel that the hurricane needs. It needs a lot of heat and a big swath of ocean. And so the death of a hurricane, all things must pass. That's why I threw the George Harrison album up there. Great listen if you ever want to listen to music. No, it's a good album. But eventually, these things can't last forever. They're going to weaken and they're going to die. And so hurricanes can exist for weeks out in the open ocean. Well, when you have that visual like we saw, all that warm water, all that moisture, they can just feed for a long, long time. But eventually, you're going to have like a small perturbance, a little different ingredient in this recipe, if you will, that will just wipe out the hurricane like that. It's kind of like we didn't get to talk too much about like stars, but like stars can exist for billions of years. But once they consume their fuel and start to make iron, they are dead within minutes. And it's kind of like whoa, what happened here? So kind of like taking a cell phone away from a teenager, like the smallest change is just going to react in like a meltdown for the hurricane. The hurricane's going to be like, I'm not doing this anymore. I'm out of here. And so the most common ends to a hurricane are both geography and cold water. And so the death by geography, so this was when we had Hurricane Dorian not too long ago. As it was coming into Florida here, man, this was like I think this was like a Category 5 as it was approaching. So recall the recipe for the hurricane was warm water and hot and humid conditions. So when a hurricane passes over land, it loses that fuel source of that really hot, moist water. Well, now it's passing over land, which doesn't, retain heat very well, and there's not moisture. And so it has no more fuel. It's like in your car, it runs out of fuel, it ain't going to go no more. And so those land masses have what I put in there, like extreme diurnal changes, like we were talking about with the desert. Very hot in the day, very cold at night. Well, when it gets cold, that's one of the things that will kill off a hurricane. So at this point, it sort of just dumps all of its rain out and has no sort of source in which it can reload the moisture, and it just sort of works its way out. It's like a kid who's having a tantrum, just getting tired. They don't have the energy anymore. They don't have the fuel to keep up the tantrum. Same with the hurricane. Now, the death by cooler waters. So this is when we had Hurricane Juliet off of the coast of Baja California over here. But anyway, it's just basic kinetics say that temperature is just a measure of motion. And so high temperature means more motion. Low temperature means less motion. And so that's all because the particles in a higher temperature are less densely packed. So the air is less dense, to whereas cold air, it's more tightly packed and it's very dense. But as the hurricane passes over cooler waters, it encounters heavier air and water. So since that heavier air and water is now present, its ability to sort of take up more fuel, being like the water and the hot water, is killed. It can't pull it up, and therefore it does not have the juice to go anymore. It doesn't have the fuel, and it is inhibited by the heat mechanism, which is not getting the heat and the moisture that it needs, and the hurricane dies out. And those are the two ways hurricanes can die. And these are the typical paths that we see of North Atlantic tropical storms and cyclones. They will form off this eastern coast of Africa. They will make their way over to these really, really warm waters over here. And man, oh man, do they get powerful. And then as they sort of hit land, you can see like the usual stopping points. Once they go over land here, they kind of die out. And some of them, sort of swing their way all the way over to, these European parts. But even when they get over to like this area, they're encountering really cold water at these really higher latitudes, and they will die out. And so I think I think maybe Dorian was able to hit Ireland, which like up here around this area. But otherwise, they typically don't do much damage over here because they've lost all their fuel. Now the fun part, playing the name game. So we had Katrina, Igor, Irma, Sandy, Andrew, Ivan, Arthur, Gustav, Dorian, Juliet. All of those are our names, but how do they get their names? Typically in science, if you discover it, you get to name it, but hurricanes are a little bit different. So they used to name them based off of longitude and latitude, being like, oh, this is, hurricane, 10 degrees north and 160 degrees, east. No, that's way too complicated. So then they used to use the Greek alphabet, which would be like, this is hurricane alpha, beta, gamma. And that really doesn't work very well because if you cycle through them, then you have two of the same name. And then if you use the same ones every year, it gets harder to differentiate. And so in the early 50s, they decided to start using like actual names, like people's names. And at first it was strictly female names, which is kind of messed up. And, men do just as much damage. And so it was then decided around 1978 that they were going to use both male and female names. So that's when, naming hurricanes actually became more equitable. And they just alternate alphabetically, meaning the first one of the year might be a male name A. The second one might be a female name with B. And then male name C, female name D. And they go on and on and on. So the hurricanes that sort of have like massive death and destruction have their names retired. It's sort of like there will never ever be another Hurricane Katrina. They're not going to recycle that one. That was too intense. We'll say they make the Hall of Infamy because we don't want to say like they're famous, but like they're so devastating that they get their own name and it gets retired. And so here you go. Now the last time I sort of did this lecture was around 2019. That's why I have it started there. But they name these storms about 7 years in advance. There's like a 7-year rotation. And so in 2021, whenever we get the first hurricane of the season, it will be named Hurricane Ana. And then the next one that forms will be Hurricane Bill, then Hurricane Claudette, Danny, Elsa, Fred, Grace, Henry, going the whole way through, all the way until they sort of reach the bottom. And then they go back up to the top and they'll use like other names as well. But you can see, going through this, just how they're named. And they're typically on a 7-year rotation. And if you don't see your name on there, you can request to have it added to the list. So that way, say if in 2021 Hurricane Ida is just massive and does a lot of damage, they might retire it. Well, if your name is like, I choose Ida. I names are hard. And there's already been like a Hurricane Ivan. There's already been Igor. An I name. The pressure's on me now, so I'm going to go to something else. Here we go. Say if Julian. Say if Hurricane Julian was huge and massive and they retired it, then they would have to put another name in there. Maybe then I would be able to get like Hurricane Jason on there. But it's sort of kind of hard to get on there because they have these rotations. And so 2005 to present, when they started doing this, there has still not been a Hurricane Jason, and I say except for the one you see before you, because I know these lectures are kind of wild whirlwinds of information. So if you see yours on there, let's see. If you see yours on there, that's pretty cool. You can wait out your own hurricane. Now, there's other naming systems. So in that's pretty much for the Atlantic Ocean storms that form. But you also have the Eastern North Pacific names. And these ones, once again, sort of rotate. And you can see on here what they will be named. And so Hurricane Juliet here, so this was probably done in 19. Yep. So this was done in 2019. So that was Hurricane Juliet right there. Or, tropical cyclone, Juliet. And then also the North Pacific, they do it a little bit different. They go based off of, I believe these are flower names of more like the like Pacific Islander like names for different flowers. They use the sort of rotation there. But I notice they don't go alphabetically. They just have different flowers that they're going to call them. Eventually, you think you're going to like run out of flowers, but who knows? Who knows? And so there you go. Behold the hurricane. These things get massive. This is from the space station. I mean, you're talking huge systems on Earth that sort of incorporate a lot of the stuff that we've talked about. Not only like differences in pressure, differences in density, the Coriolis effect, convection cycles, just a lot of stuff we've talked about. So hope you made it to the end of this. If you did, very, very proud of all of you, everything you've done. And I will see you on Thursday, maybe. But otherwise, thank you for sticking with me throughout the lecture, and enjoy.